Everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Vadum with Atlanta Functional Programming. Today we're going to be continuing our discussion of Chapter 10 of Paradigms of Artificial Intelligence Programming, Case Studies in Common Lisp, which deals with low-level efficiency issues in Common Lisp. That is, if you've entertained or even implemented, say, many of the optimization techniques that were mentioned in Chapter 9, this chapter will allow you to even further optimize your code so you can get the biggest performance benefits out of your Common Lisp implementation that you're using. Now, last week we covered 10.1 of this book, which was this chapter that is, which was dealing with specifically data types and actually adding types to your code. Type annotations is a topic, of course, we've covered quite a bit on this channel and under trying to understand in many cases when and where using type declarations will give you the biggest bang for your buck. Of course, last week I've also ended the discussion with a couple of the common um, discussion points related to um, just dealing with type declarations, run type checks, boxed and unboxed representations, and so forth. And I also mentioned at the end, as you can see, we ended our discussion with kind of how to help the compiler with some of the standard um, type declarations that you could leverage. And we also talked about the differences between, and this is just by happenstance, using, say, um, one second, um, declaim versus declare, and when and where to use either or in our code. Sorry. So today, I thought we'll, before we begin, also touch base on Section 10.2, just very briefly, because although this is a very short section and the author, Dr. Norvig, doesn't actually go through too much of it, because by now we've seen enough examples where hopefully it's clear that this technique or this tip should be obvious. In case it isn't as obvious as some folks may think, I think it would be important for us to understand when and where to apply this. And that is the tip of avoiding generic functions and using, based on particular use cases, the appropriate function that you would be dealing with. Um, to start out the example for okay, just to make things a little bit easier for us, we will of course do a very simple map vector just to get ourselves like some sample data. Um, just a simple example of grabbing the same data in two different forms, of course, and we'll actually go ahead and do a loop for I up to 10, collecting I, and we're going to go ahead and set this into a variable test vector, and we will also make the same, but we're going to also make a test list too as well for the sake of our discussion. Um, and this is going to be our uh, test list, and this is going to be what we had earlier, which is loop for I up to 10, collecting I. Okay. So you could see here, for example, our test vector is going to be a vector, and our test list is a list. And even here, I'm going to also make a string too as well. Test string, and just do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, of course, this string here, you would have to be a little careful on what this is going to be representing, and we'll see that in a minute. Now, when you're dealing with generic functions, right, as many of you know, generic functions don't really, it behind the scenes actually figures out the type information for that particular object that's passed in, and then based on its type, dispatches to the appropriate um, collection method. Okay. Uh, Hopefully most of you have seen, based on our previous episodes, that Common Lisp not only includes these generic methods, ELT, which is what we're going to see in this example, for grabbing an element from a sequence, but also SVRef if you're dealing with simple references, AREF if you're dealing with arrays and actual proper vectors with the fill pointer, a whatchamacallit, character, okay, if you're dealing with trying to get a specific character from a string and so forth. Uh, One way of writing a lot of these code could very well be, okay, we could just write, for example, ELT, say, test vector 0, or let's say 1 to make things a little bit interesting. And you could see that if we wanted to change this from um, vector to list, we could certainly do so, and we will actually get the same code result. Although in the case of string, because remember this is a string, it's actually going to give you the space character because that is actually the second element in that string, the second character in that string, even though we have commas in there. Um, it's interesting to note that while this is kind of very flexible and gives you the most structure, well, honestly, it's going to be the most flexibility in your code. Okay, so you will actually be able to change the data and do some rapid prototyping on it. When you're starting to profile your code, you're going to end up quickly recognizing that this alone is going to be a bit of a problem. And so what ends up happening is you end up doing something, you end up realizing just by sheerly disassembling this example, um, ELT, actually I'm going to have to do lambda ELT test. Actually, you know what? I don't think I need to be able to do. I could just probably just call ELT directly. Let me try this. ELT test vector test vector 1. Okay, and let's actually get the function call correctly. And if we disassemble this, okay, I have to do, fine, I have to make this into a function call because it's trying to evaluate um, the ELT function call rather than actually dealing with what we wanted to deal with. Um, so if we look at this disassembly for this particular code, you'll end up realizing very quickly that we've added a bunch of generic operations here. Okay, and this is unnecessary, not unnecessary, it's safety for the purposes of actually determining the type information so that ELT does the right thing. Okay, so if you look at line at memory code 52 here, you can see that right now we're passing in the test vector into ultimately the stack. We also add the index of the actual code representing 1 to actually be in the registers. And then we ultimately call, after moving the function pointer here on 6D of the element function, we actually call the jump instruction here, right? This is all basically setup of actually creating the function call. And because all this type information is needed is why we end up calling this function, which if we actually go look at the costs of compiling this function, it's going to be um, fairly expensive given the number of checks it's going to have to do to determine which one is the right um, change of the, well, which if we actually specify the type. One way to improve this, of course, is the following. We could just specify the type. Here, so let's first make sure we get the right type. Type of test vector. And you can see that this is a simple vector of 11. So we could just simply say, and this call here, we could wrap CWR with what we learned last time, and we could just say simple vector. And we guarantee that this is a simple vector. And we could see that already we are changing the structure of the code that's actually being passed in, right? Naturally, there's some additional tests here to make sure that um, the test vector itself is a simple vector, otherwise it throws it away. But the main stuff that you want to look at is just the code that they're using to actually uh, get the element, which is if I'm not mistaken, right around here in L1. It actually goes in and moves, essentially does a pointer offset based on where the uh, vector represents, and it goes in and moves into the the +9, which is 8 bytes to actually go and find the next character to actually go in and uh, retrieve. And then it will move that to RDX. RDX is the return register. We could then leave and actually get that off of RDX. Okay. Um, you could even go a little bit further by just calling instead of doing this, because this is all additional overhead. If you know that you're always going to be using a simple vector, okay, like in this case, you could just simply say svref, okay, svref takes the simple vector 1, and you could see here it will just give you the code that we saw earlier, okay. And this is not actually optimized for speed, of course. I could certainly try and optimize it by saying declare optimize safety 0, speed 3, and we could see that it even further reduces it here. Now let's see if we can if we compare this code here that you just saw with ELT vector 1. Okay, you can see that there's still additional number of checks before it can actually um, adjust itself to actually retrieve. The main difference is, of course, and let me see if I can actually pull my buffer up to show you this difference. Um, in one case, we are setting up the stack frame and calling the function, and in the other case, we're just doing a pointer offset. All right, and I don't think I have to explain or convince you that the pointer offset calculation and retrieval will be much faster than the function call. So this is one of the reasons why knowing when to use um, the type declarations and when to use generic functions become versus using specific versions becomes important. You will understand it, and as time goes on and as you start profiling your Common Lisp code, this will become more and more habitual. All right. This actually leads an interesting segue into our next topic, actually, which is on the topic of using complex argument lists. Okay. Um, so a brief refresher for folks who may or may not have visited our discussions on this or encountered it in their own Common Lisp development. As most of you may know, if not, this is welcome to this discussion. Common Lisp arguments, especially function arguments, contains different types of arguments. You could have uh, no keywordless arguments, where the positional arguments are going to be determining what, based on the position of the argument, determines which argument variable it's bound to. Uh, we have rest arguments, which basically collects everything after all the keywordless arguments and collects them into a single list. Then we have optional arguments. Optional arguments, of course, are, as the name sounds, are optional. And you can also provide default values for these arguments. And then there are keyword arguments, which allows you to specify the specific keyword that determines the value that it is going to be bound to. Um, According to, and this is something I wanted to at least explore a little bit with SPCL today. According to Norvig, even in 1990 or 91, when this book was published, the use of functions with keyword arguments are probably going to suffer the largest in terms of overhead when it's coming to compiling code, as well as uh, generating very efficient code, right? Um, Optional arguments and rest arguments are also going to suffer a bit, but they're not as much as um, complex arguments. Now, his order is basically, and this is something I wanted to explore to see if this is still true, is keyword functions are going to be worse than optional, which is more or less equivalent. All right. Tilde means more or less equivalent. I'm going to say it's approximately equal to, okay, in terms of cost, um, uh, rest arguments. And then this is going to be definitely worse than just positional, what we traditionally call positional arguments inside of a function signature. I'm not entirely sure where how true this is nowadays. So I thought we could do some experimentation just to see if this still holds in terms of number of instructions that are being passed. The experiments that he did was on TI Explorer. I'm sure that this still holds today. But rather than blindly kind of show expecting that, let's try out the different things here. So we have first our regular function, call this ABCD. This is going to hold, it's just going to return this as a list. Okay, very generic, nothing spectacular about this. Okay, and then we're going to have now, let's try the rest case, which he calls RST to avoid. Then you have ABC rest D. And then, of course, since you're going to do that, you can't just do list. You have to do list star. And then you can see what this does. A, B, C, and D. Okay, so we have this. So this basically looks like this. Rest 1, 2, 3, 4, 5. And then you see that it flattens it. Regular is just going to just give you, of course, 1, 2, 3. And then you have just 1, 2, 3, 4. Then you have your optional OP. We have A, B. Let's default C to 1, as the book has, and let's do D also being, default. Book has some complex calculation like the square root of A. And of course, what this is going to do is just also do a list. Okay, all these are basically list functions. Okay, now, oh, I forgot to write optional. Okay, so all of these functions are optional. So now, so if we do this and we do um, opt, for example, we get a debugging error because of the fact that square root of a can't actually be computed. So you have to do at least a minimal. Oops. Did I just kill my... Oops. Sorry, folks. Give me a second here. I accidentally killed my Lisp session. Okay. Let's do this. Connections. 1 second. Slide, restart, inferior Lisp. There we go. Starting the Lisp process. Okay, slide quit Lisp. Give me a second here. Okay, and we go. We're back. Okay, so let's do this. Shift G, that MCR, everything is loaded. And let's do one more thing. Let's add the keyword argument version. And the keyword argument version is also going to be the previous one. It'll have the same argument list as the previous one, except, actually, you know what, I could just do this. Y to Y, paste, let's call this key, and cut this to key. Right? Yeah, okay, good. We are good. So now with this one, the difference is of course with opt, you have to at least give, say, opt4 here. You see 1 nil 1 2. Here with key, you're going to have to say a. We do a1. You'll see a is 1 1, so forth. If we do 2, obviously square root of 2 and so forth. What is the difference between these? Obviously becomes the next question. Now, if we disassemble, say, let's start with the simplest one, which is regular. This one should be pretty straightforward in terms of what we kind of expected. It's generating the stack pointers, all right? Well, it's retrieving actually the information from the function frame, the stack frame that it was passed into, adding them into um, the stack for actually calling ultimately the list function, which is ultimately a call to cons. Yeah, right here is where it does. I think is the right around here is where it does the cons call. But these are all there. Actually, I'm kind of curious now. Okay, we'll see what the difference is, and then we'll go ahead and look at the actual whatchamacallit, the optimized versions of these. See what happens with those in terms of the optional and the regular functions. Okay. Optional is going to be slightly different than this if we actually go look at the version. Okay. I'm only looking at the number of bytes of the assembly just for the time being. But if we look at optional, you can see that it's just slightly equivalent. It's actually equivalent, but it's just slightly different in terms of what it's actually dealing with. There's an additional check here just to see if anything that was passed in. So in the case of A, we have a little bit of a problem because it has to do a check to make sure that when it's computing D and throwing it onto the stack, it's not nil. Um, and in this case, there's an error that gets thrown out somewhere here. I think it's in L2, jump L2, and it's the trap instruction, and because there's some allocation problem to actually go and push everything out. But the rest of the code will look exactly like the original regular function that we had. Same thing actually goes with REST in terms of the REST arguments. There isn't a whole lot that list st does, except that it may end up, it adds this call here to take the REST and flatten it, just listify REST, and then ultimately that's going to be used to actually get the information to actually create the list itself. But a lot of these other ones is pretty much roughly the same. Now notice that the difference between optional and REST, I said they were approximately equal, and the reason I say that is this is, if I'm not mistaken, if I understood the book correctly, this is going to be Lisp implementation dependent. So this is what SBCL generates. It's others optional might be better than REST. I don't know. Um, I'm only going to give you what SBCL provides us for today's discussion. But both of these are going to be better than our keyword arguments, because you could see here that to just do keywords, we need a lot of tests. And that's because, if I understood the book correctly, um, the way keyword arguments are implemented, is in here somewhere. There is a instruction that effectively gives you uh, the a store keyword. All right, and so that is because, when keywords are not bound, okay, because each keyword is essentially a variable that needs to be bound, okay, it has to be able to throw a no key error effectively, or provide some sort of default value, as you saw in the case of uh, uh, B, when we actually called key with B with no argument for B. Okay, but there's additional stuff here that we have to kind of know. This logic, you don't need to necessarily understand all this assembly code, but know that in here somewhere there are these calls to um, additional like pointers that and additional tests, mainly to deal with the fact that keyword arguments aren't just um, they're, you could put them in any order. So you could say b equals 3, a equals 4, c equals 5, and you'll still end up getting the same ordering. So this code has to understand all the different potential variations that you will potentially encounter in your keyword argument invocation. So to address this, you could create a you could do something like a inline key. This is what they were suggesting, and this is something that I have to check out to see if to try out and see what this is. But basically, you can use the proclaim form to um, inline a particular um, function. And what this, well, a function argument list. And what this does is this will actually change, but in order for me to do that, I have to actually create another function that actually does the code. So this book was suggesting we create this. No key, we have the positional arguments, which actually, in retrospect, we don't need to even do that. We could just say this calls regular. Okay. And so we have this, because sorry, I have to do this, and we have that. So now we're redefining key. And here is before we proclaimed it, 166, what, 166 bytes? Yeah, 166 bytes is our proclaim. Now, if we disassemble key, what would be the value? This would be automatically shrinking to 91 bytes. So we now have a little bit above a 50% reduction. It's about a 40% reduction in the code. Okay, we could go even further for doing some of this stuff, but this here, if we also proclaimed inline reg, we could probably see some additional benefits. So inline reg for the regular, and if we do that as well, and then let's do this as well. Ooh, what was this warning? Could not be inline because its source code was not saved. Oh, because, got it. Because I did this and then did this, it did not like that. Okay. So here we have to actually have, we're going to inline this. This is interesting. The book was suggesting that we could inline both. One. So the idea is you could create a new function that basically makes a an inline version and a non-inline, well, not an inline version, not an inline version, a a regular function like regular, okay, and um, a inline version of the keyword function, and it will ultimately um, what's it the it'll ultimately convert these functions into something that would give you that code reduction that you saw earlier. So you could still have a keyword interface, but the keyword interface is actually going to be ultimately dispatching to a non-keyword version of the same function. So the keyword version is nothing more than a facade over or an adapter to the actual function call that you're ultimately going to be calling. And this will ultimately allow you to do some interesting pieces of information. Um, Now, instead of proclaiming and doing this macro version, they actually suggested to write a macro. I'm not going to go through it here. I like the second idea, the alternative, because um, the alternative to proclaiming is just to proclaim the function that uses key to be inlined. And you could do that by um, ultimately just be able to go through the function and be able to also create a a function call that has the proclamation internal to to the actual function definition. So the example that the book brings up is something called the member function. Okay, this member function here is a pretty interesting one. Actually, you know what? Let let me go through this and this way we could do a compare and contrast. I'm going to first grab the macro. Give me a second here so I don't mess up this macro, because this is a fairly involved macro and I'm almost certain that I'll mess it up. Give me a second here. Get this from my notes. Copy. And then hopefully this is going to paste correctly. If not, we're going to have some problems. Okay, as I suspected, going to have to do some interesting funniness. Let's do this, this. Okay, to do this, S space D, and then we go there, then that, and then go this here, get this in here, and interface done. Done here. Then this is in line 2 as well. And okay, finished. Okay. So let's go and make sure that this is all proper. And we can actually go through this quickly. My apologies, folks. This is something sometimes happens when I convert to my notes. Okay. Let's see if I could do this. Okay. Symbol function name. Wait. See something here? Yeah, that's fine. No key. Let be no key function name. Be the symbol function name and no key. Okay. Let's do this. This is not going to end well, but we'll see. We'll go ahead and remove. Ooh, that's not where I want. I want this. Go there first. Map car, first or self. Set difference. Argument list. Actually, hold on 1 second. Do I have a function called first or self here already provided? Don't believe I actually wrote some of this stuff here. Okay, so this might require me to actually load PAIP into my Lisp image. Give me a second here. In the meantime, if you have any questions, anybody, feel free to post, and I will answer them once I see them. Okay, so let's see here. Not this, not this. Quick load PIP. Okay. Set package. PIP. Let's see here. First or self is here. X. Okay. describe first yourself. Okay. Yeah, it's a compiled function. That's what I thought. Okay. Let's go ahead and first correct this by making this. Okay. Arglist lambda. Okay. So there's a lot of helper functions that Dr. Norvig wrote that I'm just taking advantage of here. Um, this is just for our review sake. Of course, you could write some more advanced macros like this on your own, but we'll deal with different versions of this kind of like exercise at a later point. Um, once we get our bearings on how some of this kind of stuff works. Um, and this is a bit of an older style on also how you would probably write this macro, just mainly because some of the stuff that's in here, of course, are things that um, have been changed. If you actually read Practical Common Lisp, especially, for example, the dot comma versus I believe you could just use comma at to do the unbinding. Sorry, the unquoting of a list. So so again, I will try and change these accordingly as we go through this. But certainly this is just as fine. And this is of course creating our function body here. Oh, wait. Okay, so let us do this one. Let's load that. This, and we are good to go. Okay, so let's indent everything. Also, we need to fix this too as well, don't we? So let's do this. Arglist. Press body. Okay. So here we also have one more thing that seems to be missing, which is, okay, let's see here. If not, let's see, progen here is no keyframe, and we're inlining keyframe. Then we get the argument list here. Oh, wait. There we go. This should be it. Comment. Got it. So this is, ooh, wrong. Okay, so we are missing, oh, this here. This one is also a parentheses, isn't it? Yes. This is all parentheses. Okay. This and this. Okay. And now this is in the let. But there's one more function that we need to also handle. There is another one here somewhere. Give me a second here. This does not have a let if and okay, hold on. Let's go to here. So if it's a member and not an argument list, if of the keyword argument list. Oops, sorry. Okay, and if and not a member of the rest. Okay, now let's see here. We created functions here. And we have a let, hold on, this is not, this is going to be a problem, 1 second. Define star, function name, argument list, at rest here. Okay, so let's do this. We need to kind of, the indenting is all wrong, so let's try and get all the indenting right, shall we? Okay, so we grabbed the map car. Okay, that is the lambda list keywords and the set difference between the first herself. Then we proclaim that the inline function is here. We get the no inline keyframe name. We're defining our function. Oh, here it is. I forgot to add here that. And then this will get it. Otherwise, we have that. Okay. Okay. There's a couple of things there, a couple of parentheses that are missing here due to copying this code over. So bear with me. Yeah. So this here. There we go. Otherwise, there we go. Okay. Boom. Now we have everything right. So let's quickly review this and see how this will potentially work. Comma, not inside of a back quote. You see, this is kind of the stuff that I was kind of expecting. Line 12 on column 30. Wait a second. Caught error read. Hold on. This. What is the error? Column inside of a back row. Oh, line 70. Line 70. Okay. Go to 70. Ah, back quote. Now we got, what is it now? 75. Okay. And there we go. Now this dot comma again, like I said, I could easily switch this to comma at, but they do effectively the same thing because dot in this case is a comma splice operator, but this also does the same thing. So we could change this stuff here, but let's see how this looks for the first round. Okay, so now what we could do is we could effectively do what we did earlier, which is let's do a macro expand of the following. Of course, I'm just going to quickly do it here instead. Macro expand. Well, we don't even have to do that. We could just do defund star. Well, let's just yoink what we had earlier. Y shift it, convert this into a defund star because it's the same code effectively. And it's just going to make a version of this code that I'm creating here. If we just made this list, for example, as we had before, and we did a macro expansion, you could see that it would actually create the version of the macro expansion for us, um, which is kind of nice. Uh, and it'll then also, on top of the proc claim that we saw, it generates a second function for us. Okay, this is kind of the stuff that you would additionally habitually do when you are starting to refactor and generate some of this code. Of course, like I mentioned before, the other option, which is a simpler option, is just to simply uh, make a version that would um, inline it for you. Okay, so just inline the keyword argument that you're using. So um, if you look at the book of the book mentions like the member functions in the Common Lisp implementation, in which I think SBCL is no exception because it comes from CMUCL, which the book actually directly refers to. The member function, which looks to see if something is a member of a particular list, based on some sort of keyword function that you passed. That key is actually inline. So it's particularly interesting, and you can actually change the key that, say, if we're using first letter uh, list, it will actually try and inline the code into um, the member function directly, and when it gets called, and then it'll work. Uh, in general, for large scale refactoring specific to efficiency issues, okay, um, unless you really need to, the book basically says for most systems, it has a stand against using keyword argument in frequently used functions. Okay, uh, so at the lower level, I think that he's mentioning it because based on what I understood in the book, um, his suggestion is create a keyword interface, but internally have a lower at the lower level optimize those constraints and dispatch to keywordless versions. So this way, uh, your interface from a usability standpoint, from a maintainability standpoint, is much more flexible for your users, but internally they're as optimized as possible. Okay, does that make sense? All right. Um, Oh, it's 18 minutes. I don't know if I have enough time to cover 10.4. I'm just going to briefly mention this, and then we can have a talk about this next time. Uh, but we'll be talking about, and this is going to be a bit of again another deep dive, the use of consing, because this 10.4 and 10.5 kind of go hand in hand together, because 10.4 is talking about avoiding unnecessary consing, and 10.5 is actually talking about um, choosing the right data structure. And in 10.4 especially, there are examples in here that I don't think I have enough time to do it justice, about that when how you would end up avoiding consing and what use cases you'll end up encountering. It has some pretty simple examples that we should cover. One of which is related to our pattern matching code that we've written before in the past, but uh, it is it's going to require a little bit more of a discussion. Um, so sorry for the short episode today. Um, we will reconvene next Monday. I hope you guys all have a good Monday evening. And just a reminder, if you like our videos, please like and subscribe to the Atlanta Functional Programming YouTube channel for updates on not just Common Lisp Study Group related stuff, but upcoming talks and so forth. And of course, for those of you who are in the Atlanta area, Atlanta Functional Programming is looking for speakers both for our in-person meetups as well as our online meetups. If you have a topic, anything functional programming related, and this is a announcement to anybody who's out there who's watching our videos. Um, if you are outside the Atlanta area, we could schedule you for an online talk. If you're in the Atlanta area, by all means, talk to me or Judd. We are on Tech 404 as well as functionalprogramming.slack. Reach out to us with your topics and we will get you scheduled. Also, for those of you who are in the Atlanta area, this is an announcement for you. Atlanta Functional Programming is looking for a new home uh, to have our in-person meetups. We have kind of been without a home since the pandemic, and we are willing to have in-person meetups at a standard venue. Uh, just again, reach out to either me or Judd and let us know your suggestions, and we'll take a look at your place. And hopefully, we can come to some sort of agreement to host our meetups there. Um, Again, look out to meetup.com. For those of you who are our subscribers, if you're not, please register for our meetup for announcements there for upcoming talks. And with that, I wish you all a good Monday night. Thank you for joining us.